Welcome to Deep Tech Dharma, an autonomy thesis. Right now, there is this invisible gas that is quietly responsible for up to 2% of the entire world's carbon footprint.
Yeah, it's massive.
Right. And you have probably never bought it, you've never seen it, but without it, I mean, modern industry would literally collapse overnight. It refines the petrol in your car, it makes the fertilizer that grows your food, and it is, entirely fundamental to producing the steel holding up the building you're in right now.
It really is the ultimate behind-the-scenes operator. I mean, the global economy is completely structurally dependent on it.
Absolutely.
But because it operates so deep inside these heavy industrial supply chains, it remains almost entirely out of sight for the average consumer.
Yeah, but today we are bringing it into the light. We are going deep into the hidden architecture of the industrial world. We're looking at a stack of technical briefings, startup profiles, and some policy data centered on a Bengaluru-based deep tech startup called Newtrace. And the mission of this deep dive is to unpack how two engineers are attempting to fundamentally redesign a single, highly obscure machine. And they're doing this to break India's massive dependence on foreign energy and foreign materials.
What's fascinating here is that this isn't just a story about clean energy or, hitting emission targets.
Right, it's bigger than that.
Exactly. It is a story about true sovereign capability. It's about the mechanics of building a nation's energy independence from the ground up, using its own materials, rather than just swapping out one geopolitical vulnerability for a brand new one.
For a different one, exactly. And for you listening, I promise this journey is going to change how you look at the physical infrastructure we all just sort of take for granted.
It really will.
So to start, we need to look at this invisible giant, which is hydrogen. India burns through roughly 6 to 7 million tons of hydrogen every single year. And that number is, it's climbing fast.
It is, and the critical context isn't just the sheer volume, it's the origin. I mean, we all know the basics of the energy transition, but the industry currently uses what's called gray hydrogen, which is extracted from natural gas or coal through these incredibly carbon-intensive processes.
So it's dirty from the start.
Very dirty. The carbon footprint is essentially baked right into the fertilizer or the steel before it ever leaves the factory.
Wow.
The alternative is green hydrogen, which is splitting water into hydrogen and oxygen using renewable electricity. So zero emissions.
Okay, let's unpack this. If we have a zero-emission way to make the exact same gas that powers all these massive industries, why is it still struggling to take over?
No.
Like, if I'm running a steel plant and I know the green version exists, why am I still buying the dirty stuff?
It comes down to raw, unforgiving economics. Historically, green hydrogen has cost roughly 3 times as much to produce as gray hydrogen.
3 times.
Yeah. And in industries like steel or fertilizer manufacturing, your margins are razor thin to begin with.
Right, they can't absorb that cost.
Exactly. A foundational raw material that costs 3 times as much isn't just expensive, it's a complete non-starter. It would bankrupt the operation.
So like a physical wall.
Yeah, it's a physical barrier, this microscopic sieve inside the machine that allows certain ions to pass through while keeping the hydrogen and oxygen strictly separated.
But this membrane isn't just a simple piece of plastic, right? It sounds like it's a highly complex bottleneck all on its own.
Oh, it is incredibly complex, highly fragile, and very expensive. It degrades over time, it requires ultra-pure water, or it basically fouls and ruins the machine.
Jeez.
Furthermore, these traditional high-efficiency systems operate in a highly acidic environment.
Acidic? Wait, why does that matter?
Because if the inside of your machine is highly acidic, you can't just use standard stainless steel or, cheap metals for the electrodes.
The parts that actually conduct the electricity into the water.
Exactly. The acid would dissolve them in hours. To survive that environment, the catalysts have to be made from highly rare, extremely expensive metals. We're talking about platinum and iridium.
Iridium. I was reading up on this before we started. Iridium is like one of the rarest elements in the Earth's crust.
It is incredibly rare.
Most of it comes from deep within the Earth's mantle or from ancient meteorite impacts, and the global supply is just unbelievably tight.
It is highly concentrated.
Yeah.
And this brings us to the real supply chain reality here.
Right.
Nearly all of these specialized polymer membranes and the rare metals like iridium, they're imported. They come from a tiny handful of global suppliers, primarily in Western nations or concentrated mining operations in places like South Africa and Russia.
If we connect this to the bigger picture, if India, or any nation really, transitions its entire heavy industry to green hydrogen using standard electrolyzer.
They're simply trading one foreign dependency for another.
Exactly. They might stop importing fossil fuels to make gray hydrogen, but they suddenly have to start importing highly specialized polymer membranes and incredibly rare earth metals just to keep the clean fuel flowing.
That's the trap.
Wait, let me push back on the conventional wisdom for a second. We hear politicians all over the world talking about energy independence because they are building domestic solar and wind farms, right?
Oh, cons.
But if the actual machines converting that power into industrial fuel require iridium that you don't have and membranes you don't manufacture, are you actually energy independent? Or have you just built a multi-billion-dollar trap for yourself?
That is the exact vulnerability that keeps energy ministers awake at night.
It has to.
You cannot claim true sovereign capability if the very heartbeat of your industrial power can be throttled by a foreign supplier holding back polymer shipments.
Or if, like, the price of iridium skyrockets by 500% on the global market because of a localized mining strike somewhere.
Precisely. And this realization, this massive, glaring supply chain vulnerability, is what prompted two engineers to completely rethink how the machine functions at a molecular level.
This is where we get to this startup.
Enter Newtrace, founded in 2020 by Prasanta Sarkar and Roshan Sinha.
Right.
Sarkar is an aerospace engineer. The story goes he was on a backpacking trip across India, taking a break, and realized he wanted to stay and tackle a genuinely foundational engineering problem rather than just working on, incremental tech.
Love that.
And Sinha is an expert in nanomaterials and electrochemistry. They crossed paths at the Entrepreneur First program.
So they looked at this triple cost problem, right? The expensive power, the fragile membrane, and the rare metals.
Right.
And they realized that trying to make the traditional PEM electrolyzer just like 5% more efficient wasn't going to break the dependency at all. The architecture itself was the flaw.
Exactly. They had to strip the machine down to its studs. Their breakthrough is a radical redesign known as a membraneless alkaline electrolyzer.
Okay, membraneless alkaline. Let's break those two words down for a second. Starting with alkaline. What does that actually change about the chemical reality of the machine?
It changes the entire battlefield. So we talked about how traditional systems use a highly acidic environment, which forces you to use platinum and iridium just to stop the machine from dissolving.
Right, the meteorite metals.
Right. Well, alkaline means they use a basic water solution, like potassium hydroxide.
Oh!
By shifting the chemistry from acid to alkaline, the environment is far less corrosive.
So by just changing the pH of the water, suddenly you don't need iridium anymore. You can use cheaper, everyday metals that don't dissolve.
That's the first major victory.
Wow.
But the bigger engineering leap is the membraneless part. They literally removed the physical barrier that separates the explosive gases.
Which brings us back to the mixing problem. If there is no physical wall, how on earth do you keep the hydrogen and the oxygen from combining and blowing the roof off the facility?
They replaced the physical wall with fluid dynamics.
Okay, tell me more.
They used the heavily calculated flow of the liquid itself to act as the barrier.
Here's where it gets really interesting. I was trying to visualize this from the technical briefings, right?
Yeah.
Instead of a physical wall, it's kind of like imagine two rivers flowing parallel to each other inside a channel. By precisely engineering the speed, the pressure, and the geometry of how the water moves, they create this dynamic where the hydrogen bubbles are violently swept to the left bank,
Right.
and the oxygen bubbles are swept to the right bank, completely pulling them apart before they ever have a chance to drift across the center line and mix.
That is an excellent way to visualize it. It's essentially advanced bubble manipulation.
Bubble manipulation, I love that.
Yeah, buoyancy, drag, and flow velocity are doing the job that an expensive piece of imported plastic used to do.
That is wild.
And to ensure absolute safety, they integrate in-house oxygen detectors that monitor the gas streams in real time. If a single oxygen bubble crosses the river, the system knows instantly.
The engineering impact of just removing that membrane is staggering. According to the data we looked at, eliminating that physical barrier removes roughly 70% of the machine's internal components. 70%.
Just think about the cascading benefits of that.
Yeah.
Less complexity means a massive reduction in assembly time. It cuts manufacturing costs by about 30% straight out of the gate.
Right, because there's just less stuff.
There are fewer parts to buy, fewer parts to assemble, and crucially, fewer parts to break.
But the real kicker here, the thing that makes this a viable industrial solution and not just, a cool science fair trick, is the efficiency.
Exactly.
Because despite removing 70% of the guts of the machine, It actually matches the electrical efficiency of conventional systems. It uses about 45 to 50 kilowatt hours of electricity to produce 1 kilogram of ultra-pure hydrogen gas.
So they successfully eliminated the membrane dependency. But they didn't stop there. They opened a second front to attack the metal dependency we talked about earlier.
Okay, because even in an alkaline environment, you still need a catalyst to make the chemical reaction happen fast enough to be commercially viable at scale.
Right. Otherwise, your rivers are just flowing without producing enough fuel.
Yeah.
This is where their proprietary technology, voltagen, comes into play.
Voltagen.
The briefings describe it as a drop-in electrode technology.
What does that mean in practice?
Well, voltagen is their custom-designed catalyst. Because they are in an alkaline environment, voltagen is formulated entirely from abundant earth metal-based materials.
Metals that can be sourced locally within India.
Exactly. No platinum, no iridium, no supply chain chokeholds.
It's essentially like a universal engine block. You don't have to redesign the entire industrial setup around it.
Right.
You just drop in this locally sourced, highly efficient engine block, the voltagen electrode, and suddenly your electrolyzer is running more efficiently, completely free of the rare metal bottleneck.
Yes, and the numbers back that up. In fact, the data shows this new catalyst cuts the specific energy use by up to roughly 9.5 kilowatt hours per kilogram of hydrogen.
That is a massive saving at scale.
It attacks the double dependency simultaneously and aggressively. But having a brilliant, efficient machine on a workbench in Bengaluru is one thing. Hydrogen, as we established at the start, is a game of heavy, unforgiving industry.
Yeah, it's not consumer tech.
No. To truly break a national dependency, you can't build consumer gadgets. You have to deploy this technology into the belly of the beast.
And Newtrace aimed squarely at the giants. I mean, they aren't building small units for Bluetooth applications. They are targeting refineries, steel manufacturing plants, and large-scale fertilizer producers.
The industries where the carbon footprint is the absolute worst.
Exactly, the real heavy hitters. So where are they at right now with deployment?
They are currently running a 20-megawatt pilot facility.
Wow.
They are actively commercializing 1-megawatt systems, aggressively scaling toward 5 and 10 megawatts, and they've already bid roughly 30 megawatts into a government tender.
Okay, so what does this all mean for the listener? We throw terms like 20-megawatt pilot around pretty easily, but let's ground that. A 20-megawatt facility is not some shipping container sitting in a parking lot.
Oh, not at all.
It is serious, heavy industrial infrastructure. It's enough raw electrical power to run a small town funneled entirely into ripping water molecules apart. When you operate at that scale, you have left the laboratory completely behind. You are playing in the major leagues. Why should the listener care? Because the biggest climate wins aren't going to come from you and me buying metal straws, right? They come from cleaning up the dirtiest, most invisible factories on Earth.
And they are bringing major league partners with them to do just that. They've formed a significant partnership with Bharat Petroleum, BPCL.
That's one of the massive public sector oil and gas companies in India, right?
It is,
Yeah.
and that feels like a massive validation.
Boy.
When a legacy fossil fuel giant starts partnering with a green hydrogen deep tech startup, it signals a real tectonic shift in how the energy landscape is being viewed as the highest corporate levels.
Yeah, they see the writing on the wall.
Exactly.
Yeah.
They're also collaborating with DIFR, the Dutch Institute for Fundamental Energy Research.
Which is huge.
It really is. It adds rigorous international scientific validation to their fluid engineering models.
And we really cannot ignore the macro environment they're operating in right now. They have a massive national tailwind at their backs.
They're absolutely massive.
In January 2023, the Indian government launched the National Green Hydrogen Mission. And this is a staggering commitment of roughly 20,000 crore rupees with a hard target to produce 5 million tons of green hydrogen annually by 2030.
20,000 crore. That is a deafening financial signal to the market.
Seriously.
It basically tells heavy industry, this transition is happening, get on board right now.
And the dynamic here is incredibly unique, too. Newtrace is backed by roughly $13 million in venture capital funding from major investors like Peak XV Partners, Aviskar Capital, Special Invest, and Mycelio Fund.
Right.
The sovereign capability, the intellectual property, the radical redesign, it is entirely founder-built and VC-funded.
Yeah, the government didn't invent the membraneless fluid dynamics in a state-run lab.
Exactly. The innovation came entirely from private enterprise. But the government is acting as the ultimate financial tailwind and an early massive customer through those public sector refineries and the Solar Energy Corporation of India vendors.
It is a really potent convergence of agile private sector innovation meeting massive state-level policy goals.
It sounds like an unstoppable momentum when we lay it out like that. The tech works, the funding is there, the government wants it. But, let's pause and introduce some friction.
I have to.
Because this is deep tech, and deep tech is notoriously brutal. Disrupting an entrenched global energy supply chain is never a guaranteed win.
This raises an important question, and it really gets to the very heart of the risk involved here.
Right.
It is a highly capital-intensive endeavor. The first hurdle is sheer market economics. Green hydrogen, even with Newtrace's cheaper, membraneless machines, still has to fall sharply in overall production costs to truly beat gray hydrogen on the open, unsubsidized market.
And they aren't the only ones trying to solve this either. Newtrace is a very young company going head-to-head with massive, established, global electrolyser incumbents.
The big guys.
Yeah, we are talking about companies like Nel Hydrogen, Life, and EvoLoH. These are giants with deep pockets, massive R&D budgets, and decades of established trust relationships with the exact steel and fertilizer plants Newtrace is trying to sell to.
And that matters so much. When a steel plant manager is looking to invest hundreds of millions of dollars into new infrastructure, their primary metric isn't just cost.
It's reliability.
Exactly. They need a machine that can run 24 hours a day, 7 days a week for 20 or 30 years without a catastrophic failure.
Because an unexpected shutdown in a heavy industrial plant can cost millions of dollars a day.
Yes. So put yourself in that boardroom for a second. How does a young startup survive that pitch?
It's tough.
The incumbent points to their traditional polymer membrane machine and says, look, it's expensive, but we know it works. We have 20 years of operating data to prove it. Then Newtrace walks in and says, we took out the membrane, we use fluid rivers to separate explosive gases.
Doesn't the decades of proven uptime requirement act as like an almost insurmountable barrier to entry for a novel design like that?
It is a massive barrier. Pilots are promises, but industrial plants are proof.
Yeah.
Scaling from a highly controlled 1-megawatt system to a reliable multi-megawatt industrial plant that must operate flawlessly in a harsh, dusty, fluctuating industrial environment. It is one of the most brutal engineering tests imaginable.
Because if the fluid dynamics fail for a fraction of a second and those rivers mix, the whole facility is compromised.
That is the absolute stakes of the game.
Yeah.
So how does Newtrace win that boardroom argument?
What's their angle?
Their foundational bet is on the physics of simplicity. A machine with 70% fewer parts fundamentally has less that can break.
Right.
If you completely remove the most delicate, fragile, degradation-prone component, which is the polymer membrane, you theoretically increase the long-term durability of the entire system.
It's the ultimate counterpitch, really. Our machine is simpler, it costs 30% less to build, and because it runs on abundant local metals, you will never have to worry about a geopolitical crisis on the other side of the world shutting down your factory.
They are betting that they can win on capital expenditure and sovereign security simultaneously.
It's a smart bet.
It is, but they still have to prove that durability, day in and day out, at massive industrial scale. The next few years of deploying these 10 and 20 megawatt systems will be the ultimate crucible for them.
Which brings us to the autonomy ledger for this deep dive. Let's look at the balance sheet of what we've uncovered today.
Let's do it.
On one side, we have the immense dependency that is being broken. India's reliance on carbon-heavy fossil fuels to produce the industrial hydrogen that runs its economy. A reliance that is compounded by a dangerous double dependency on imported polymer membranes and rare earth metals just to make the clean alternative.
It's literally a bottleneck within a bottleneck.
Exactly. And on the other side of the ledger, the sovereign capability being built. A homegrown, membraneless, alkaline electrolyzer, engineered from abundant local materials.
Right.
It's an innovation that completely sidesteps the global supply chain chokeholds, allowing a country not just to generate its own clean fuel, but to physically build, own, and control the very machines that manufacture it.
The capability to build the tools, not just use them. Yep. That is the true definition of industrial independence in the 21st century.
For you listening, take a moment to really appreciate the sheer audacity of this. Two engineers meet by chance, look at a 20,000 crore national challenge, and decide that instead of just importing a Western solution, slapping a new logo on it, and calling it a day,
right,
they are going to literally strip the machine down to its core physics.
Yeah.
They rebuilt it from the ground up, utilizing the fluid flow of water and abundant local metals to solve a geopolitical vulnerability.
It is a masterclass in engineering from first principles.
Uh,
And I think it leaves us with something critical to mull over long after this discussion ends.
what's up?
For the last century, global geopolitical power was largely defined by geography. Who controlled the crude oil beneath the ground.
Sure.
But as we look at the rise of innovations like Newtrace, we have to ask, will the geopolitical power of the next century be defined by who owns the intellectual property to build the machines that harvest the elements above it?
The invisible gas and the invisible machines suddenly becoming the most important things in the world. Thank you so much for joining us on this deep dive. Keep questioning the physical architecture of the world around you and stay curious.